Hello and welcome to my first electronic project and the first milestone of actually my first electronic project because it's not really done. I wanted to sort of make this video to share with the world with what I'm doing, and if anybody wanted to learn a little bit about microelectronics or just had a slight interest and just wanted some, quick knowledge, I just wanted to put this on here just to show you how some of this works and also how an LED matrix works. And if anybody wants to follow my projects, I'll be posting videos and pictures from time to time on Facebook or my website. And this project actually, I chose my first project to be a tic-tac-toe game. I wanted to make a little tic-tac-toe electronic version with a 3x3 matrix. And I set my first milestone as actually no buttons, no input to anything, just display the LEDs. And as you can see here, I'm displaying the top three, the middle, and the bottom two. And the other LEDs are off at the time and it's not really doing anything. But I wanted to share this because I thought it was pretty interesting how LEDs are actually displayed. It's not at all what I thought, or at least I'm not doing it with what I thought would be the right way. maybe the professionals are doing it another way, but here's how I'm doing it. I thought, and it's a cost cut savings way, for cheaply, but probably at the expense of too many wires, as you can see here. So I just want to share with you of how I'm actually turning on this 3x3 LED matrix, this 2D array matrix, because it's pretty dang interesting. It's not at all what I first pictured of how I'd be able to do it. I thought I'd just be plugging in pin by pin and being able to turn on this electronically. Hey, I want to turn this one on, but that's not the case. You have to do some magic in the code. And along with these support components, the transistors, resistors, and shift registers, am I only able to actually display what LED I want on. So this video is going to be more about how this is working right here, and just give you a quick oversight of what I'm doing. In the next video, I'll probably have a button matrix up to sort of display the rest of the tic-tac-toe game, and that'll probably be it, because I can't imagine it'd be too much more and the tic-tac-toe buttons be as hard as this LED matrix. So right here I got the LED matrix on, and I have two shift registers. You'll notice the green wires from this shift register that they're connected to, which is controlled by the microcontroller on my ThinkPad, or not ThinkPad, LaunchPad. And let me actually, before I jump into that, just jumping right into things. Hey, you know all this? Yeah, okay, good. Let's jump into the LaunchPad a bit. And this is a Texas Instrument LaunchPad. They make calculators and a bunch of other electronic things. But, they make a great LaunchPad, and this is really used for development purposes. The only thing that's really being needed here is this black IC, integrated circuit, which is a microcontroller. If you ever see like a black thing, that's what's called just an integrated circuit, an IC, and it could do anything. You have to look up the part number that's etched on the top of it, and very small numbers in alphabet and characters. But really all this is doing is it's an easy to use development board. This microcontroller just basically its wires with the silver pin, with the pins, are just connected to these wires, and it just jets out over here, and with the microcontroller I just basically write some code on my laptop, transfer over to USB, which is handled by somehow magically. It's not too magical. It's pretty easy if you want to do it with yourself, but it's kind of annoying. And the code is loaded on to the microcontroller, and then as soon as it gets power, it starts executing the program, and it's getting its power from the USB. And there's a bunch of other silly little things like debugging. If you want to debug it tool, and there's a couple buttons and a couple LEDs if you want to turn off LEDs and on LEDs on the board. Just to give you some information of what's going on in the board without you having to supply your own LEDs and supply your own little thing. So nice tool. It was only $10. It was very nice, and microcontroller is this is the bottom of the line. It's called the MSP 430. 16 megahertz with 512 bytes of memory and bytes of RAM and 16 kilobytes flash. So nothing too big of a program could be put on that, but those only cost, what, I think it's 50 cents each, so worth it. Make a tic-tac-toe game of it. So okay, you know, that's the guy that's controlling it all, and you can see a huge amount of wires just going onto this board right here. Most of the wires are going onto this guy, and controls them, which control the LED matrix, which also controls these transistors. The top shift register controls with these transistors, and then it completes the circuit, if possible, by communicating to these transistors, and then going over to the ground or the negative wire, and that negative wire is connected to a negative on here, goes back in the laptop, completing a circuit. And that's how I'm trying to complete a circuit for certain LEDs. On LEDs I don't want light on, I make sure that circuit is not connected. You know, it's not completed. It's an open circuit. And that's how you sort of control your LEDs, with shift registers. Another thing about why I'm using shift registers instead of just manually getting my output pin from my microcontroller and completing a circuit by myself is this is a 3x3. I could easily do that because I got enough pins on my microcontroller. I got like what, 20 pins? That's a 3x3. That's only 9 pins that needs to use. I could easily do it, but in the end I want to go over into larger endeavors like a 12x12 matrix for a board game. I want to eventually make electronic board game, and 144 pins. There's no microcontroller out there that has 144 pins, but with shift registers, these have a maximum of 8 each, 8 pins it can control, and you could sort of chain them up to make it a massive control system. And that's one way to sort of relieve the amount of pins you need to use in your microcontroller, by using these external components, like shift registers or multiplexers. Those multiplexers almost like a shift register. And I'm going to explain the shift register process, a little bit, to complete control a whole, 1000 by 1000 matrix of LEDs. So let's jump right into it. What I'm going to do is I'm going to show you how these LEDs are being lit up by the shift registers by slowing down the speed of the microcontroller, of how fast it's controlling these shift registers. Right now it's going so fast that you can't tell that these are actually on some of the time. Because once you guys see it on a breakdown, you'll see, oh, well, those LEDs are actually on. But no, it's actually pausing for 10 milliseconds on these LEDs that are on. So it gives us the illusion, our eye can only perceive that those are actually on. And we can't actually see the other ones being on at the other times, because I think it's going faster than 70 hertz, so 70 times per second. So let me pause the video, and I'm going to bring it back on with code loaded into the microcontroller after I compile it. That'll slow this whole activity down, and you'll be able to see how these LEDs are being controlled. And I find it pretty cool. And we're back. Okay, so I added 4 more LEDs right here. So let's zoom in on this. I have to sort of hold the camera because I don't got a tripod. And you notice these 4 LEDs and this LED and this LED. Those are really just debugging stuff, so you can see what's going on. Previously you didn't really need to see these LEDs because they were always on before. But now they're not, because we're slowed down. And it's going to be hard to see which LEDs are on off, but let me just tell you that they are on. They're not all on at the same time. So I want to say these control the columns, which one vertically, and this controls which row is going to be on. And we've got to do it one at a time. We've got to do one row at a time. And you can see how the microcontroller is using these LEDs. The LEDs sort of just represent which wires are on. And these 3 bottom LEDs are connected to these 3 wires, and these 3 bottom LEDs are connected through these 3 green wires. And this top LED is called a clock, which adds 1 to the shift register, and this guy shifts it. So if you want to add a light, essentially a high electricity, you want to turn this guy on when this guy is on, and then you could see this light bulb is on, and then it moves it into the first light. And then every time this guy clicks again, it shifts it over by 1. And if this guy light isn't on, well, then it's going to and this guy turns on, then it's going to shift to 0 or nothing. And it's going to shift what else is ever down into the other thing. Oops, sorry, slipped off the table. So just to give you a vertical view, and maybe my shadow will hide some of the dimmed light from the thing. But so we see I have 2 LEDs on the bottom, and it builds up the bottom one first, and you notice no lights really turn on. And as you can see, this one's inverted. These lights are inverted. This is actually the top light right here is for the bottom, and the middle is for the middle, and the bottom LED is for the top row. So those are rows, and this is column again. So you can see it's going to turn on 2, 0, 2, and that's for the bottom row. And it wants to turn on all 3, and then it moves to the top row. And this microcontroller is sending out highs, it's electricity, to these shift register for this LED and this LED to control which 3 outputs are on. And these yellow ones go through resistors, which slow down the current so it doesn't blow out the transistors, and control these transistors which complete a circuit or not. And they complete a circuit only if the light is on, the electricity is on for them in the middle of the base. And so it's only on if this guy says it's on. So that's why you see these lights are on, but nothing of the lights are on until this guy says it's on. And then you see this shift register is controlling the comms via the green, which they're connected in the parallel. All the comms are connected in parallel in their anodes, their positive leads. Then the rows are connected in their cathodes, the negative leads, which can connect to the resistors to make sure that none of the LEDs sink in too much current to blow them up. Because if you just connect an LED to its power source, it's gonna chew up too much current, and it's gonna try to put too much current through it, and it's gonna blow up. Just like applying too much current through a light bulb, it'll just make the little thing, you'll hear it pop, and that's it. And then it connects to the input to these transistors, and then the output of the transistors, if these transistors are on, will connect to the ground, completing a circuit. So as you can see, I only could do 1 row at a time. If I try to do multiple rows, you're going to get weird signals, because you can't really tell with 3 inputs for y coordinates. This would be 3 y coordinates, which rows are on, and x coordinates. You can't really tell all the parameters at the same time. You can only go one by one, either by controlling it with the rows or controlling it by the columns. You can only have one on. So that's how I do it, and it's pretty cool. I thought I didn't really think of this all by myself, but I sort of came to the conclusion after reading stuff that this is the way to do it, very effectively too. The only problem is, of course, all these wires cost money. That's one of the big sinkholes, and to have this on a board game, I'm going to need to use wires. I can't use a copper board, because just think about a 1 foot by 1 foot copper board, and it just cost me $20. It's not worth it. I'd rather just do wires and pay $7 and spend 2 days cutting 288 individual wires and stripping the ends of them and soldering the outputs. That's actually probably the way to go. To be cheaper, but it'd be a heck of a lot slower rather than a machine doing it. And I'm using these LEDs. These LEDs will be taken off, of course, and I'll get more tighter wire so that it's not looping. I could just sort of place it like on the ground, like these white wires or the brown wires, so it's really taut against the breadboards. And I'll represent the X's again. X's will be, I guess, solid colors when I speed it up, and O's will be fast blinking colors, so I could tell who's who. And then I'll have an extra LED on this person's side and an extra LED on this person's side to tell who it is, whose turn it is. And intermix buttons in the middle, or if it's too tight or if there's too many wires, I'll just put the buttons to the side. And that'll be the first project that I do. And I'm kind of interested in getting right into the buttons part of it. But I still realize I need to do some coding just to make sure to get everything right, and everything's easy. But that's it, and that's the first part of making this Tic-Tac-Toe game, which will eventually be a whole board game. I'm looking to make a 12 by 12, and rather than, of course, jumping right into the board game and messing up, like I've done many times with this electronic project right here, that I'd rather mess up small than mess up big. Save time and money on this stuff. So all right, well, stay tuned. Just follow on Facebook or the website, and you'll see the buttons being added to Tic-Tac-Toe, and then eventually, hopefully, the board game I'm looking to make. And I've already got some of the parts or not parts, but the structure of the board game working. And I just need to sort of, you know, get this all ironed out, and then once I know how to do that, I can just jump over and do more stuff. Or I might, you know, do some extra parts of the board game like sound, even though the sound tutorial that I posted was just terrible, but who knows. I thought, you know, I hope you guys like, and you know, like and, you know, follow along on the Facebook page or website if you you want to learn more about, you know, shift registers, how these shift registers are working, or more about transistors and resistors. I'm sure that's all the parts to this project. There's not going to be too much more to it besides buttons, and that's it. Okay, well, and also I just want to mention one thing. I'm not going to jump too much into coding. Coding is pretty dry and too hard to learn. For non-tech savvy people, it's just boring. So I'd rather have something interactive showing. All right, well, I'll talk to you later and keep you posted. All right, bye.